14.2 days sounds like a week. I'm going to call that 1 week. Oh, 2 weeks. Sorry, 2 weeks. Okay, well, that makes it a little bit easier, but not a lot. The problem is that, so what does that mean? That means that you start on a certain activity in 1 week, and the question happened to be, what is how many in 1 week? And here's your 2 weeks. And let's say 3. Okay, so that means that in the activity, let me keep calling it n, will be half after 2 weeks, so that it's going to go down something like this, but with a power, that's bad drawing. Here's 2 weeks, here's n over 2. It's got to pass through here, right? Okay. The problem is that this is decaying. Yeah, I would not ask you to do this because this really requires an integral, and I haven't really ever asked you to do an integral in this course. The point is that what you would have to integrate is you want the number integrated, the rate, that n0 of t to the t over 2 minus t over t1 half dt, integrated from 0 to, what, 1 week, to roughly t1 half over 2, right? In other words, this is the rate at which it's going. The rate is constantly changing. You have to integrate that from 0 to roughly 1 week, which is roughly half of the lifetime, the half-life. So that would be the total number of, now this is how many are left. This is how many are left. Then you would subtract, this is n remaining, right? Because, oh, this may not be so bad. Wait a second. No, it may be not so bad, because we know that after 1 week, half of them are left. But half of them must have died. Oh, but half of them died in 2 weeks. It's not necessarily true that half of them have died in 1 week. Okay, let's do that. You have to then do 2 to the minus t1 half over 2 over t1 half. So it's 2 to the minus yeah. Okay, so this would be the number left after 1 week. And it would be n0 after 1 week. This would be the number left. So you subtract that from the number you started with, and that would be the total number that decayed. So it really isn't, you quite don't need to do an integral. You could just get the square root of 2, which is 1.4. So it's n0 over 1.4 r left, and subtract that from n0 minus n0 over 1.4, and that I think is how many decayed, something like that. Yeah, that's the line. I'm rushing through this. I probably maybe make a mistake, but that's the general feeling you get. Now, if the beta rays, so that's how many decayed. If the beta rays have an energy of 705 keV, what is the total amount of energy absorbed by the patient's body in 1 week? Well, if these are the number that are radiated, each of them carrying 700 keV, you just multiply 700 keV by that number. So if we have the number of emissions times the energy per emission, that will cancel out and you'll get the energy. So you just take that number, the number emitted, and multiply it by that 700 keV, 700 and something keV. Okay, does that make sense? Yeah. And find the, oh, equivalent goes in REM. Oh, somebody asked me about REM, and I don't remember what REMs are. Let's see, it's the Roentgen, as I recall, we can look it up, but Roentgen equivalent. I have not used REMs because people don't seem to use it, as I mentioned in our office. People seem to be using this other unit, the Sievert, which is, it tells you sort of the bodily effect of radiation, the Sievert. And I think the REMs are also a similar unit, but the Sievert actually makes sense. It's the amount of energy absorbed, which we just calculated here. I mean, if the person absorbed all those radiations, energy absorbed per kilogram of the person, because that would be important, how many cells the person has. That would tell you how much damage, what fraction of the cells in a way got damaged. And then, excuse me, that gets multiplied by this biological effectiveness factor, namely the RBE, which we're told is 1.5 in this case. So if I was studying this problem, I wouldn't do it in terms of REMs. I would do it in terms of this unit that seems to be more popular now. The energy absorbed per kilogram times the RBE, and the RBE, this is the relative biological effectiveness, which means how much damage it does. So these beta particles being 1.5, if they were alphas, the number might be more like 10 times larger, like 10 or 12. And so that's how I would answer that. Yeah, I think it's maybe not so bad. You just have to, now you have to do an integral. You just say, okay, I'm over here, and I divide the number, instead of dividing it by 2, the number is divided by 1.14 over n0. And over here, it's n0 over 2. No, let's see, square root of 2 is 1.4. I'm sorry, 1.414. Something like that. So there's more left after 1 week, and you just subtract that from how many you started from and get how many decayed, I think. Okay. Any more? What do we got? How long? We have till Tuesday. So what else? Yeah, we'll go over the materials well. I mean, I'd like you to be familiar with the kinds of materials we have in our world, you know, how they respond to electric and magnetic fields. We haven't gone into stuff like mechanical properties. We never talked much about brittleness. We haven't talked about strength, you know, tension or compression. We've left those mechanical properties out. But we are emphasizing electric and magnetic in this course because it's, of course, an E&M basically. And the quantum mechanical basis of these properties. We quite remarkably can understand the difference between electrical conductor and an insulator on the basis of quantum mechanics pretty well. But as I point out, because of your nice question about superconductivity, we don't know everything, and they're puzzles. It's really amazing. After 30, 40 years, we thought we understood solids pretty well, and you have the smartest guys around, and they're still fighting. What causes this major phenomenon? They use these things, these high-temperature superconductors, so their business is obviously very reasonable material. As I think I mentioned to you that the temperature less ISO is up around 100. I think it's around 120 now Kelvin, which is, in fact, Professor Cohen here, when this discovery was made, and it seemed like the world was opening up a whole new thing, he says, someday you'll be able to go to the hardware store and ask them for wire, and the guy's going to say, do you want normal or superconducting? And it hasn't happened. I mean, at room temperature, that you just walk in and buy a superconducting wire. Maybe someday, maybe one of you guys will come up with that, but so far it hasn't been done. But, 120 degrees is very, very good, because the key thing, the minimum is liquid nitrogen temperature. Because if you can cool a thing, liquid nitrogen is very cheap. It's cheaper than milk. I mean, it's like $1 a quart. A gallon is, a couple dollars or something for liquid nitrogen. So if you could cool a thing with liquid nitrogen, which is 77 Kelvin, and you could get a superconductor, it sounded like heaven, because it's cheap, and if you get rid of all electrical resistance, it sounds wonderful. But as I mentioned when I first talked about these high TC things, it's a funny material, yttrium, barium, copper oxide. It turns out it's very brittle. It's hard to make into wires, because you got to draw out a wire and it'll crack. And so it hasn't quite been as easy as we hoped, but it's still pretty good. And for some things, like for example, I think probably for things like we need to put a lot of current through wires and get like a big magnetic field, like an MRI machine. These superconductor wires are very good. You just throw in liquid nitrogen, cheap stuff, cool it down, and then you don't have to use so much electrical energy to keep the current going. So it's a big breakthrough on those applications. But we still can't go into the hardware store and just pick up a spool of superconducting wire and take it home and put it in our house and say, oh, there'll be no electrical resistance in the house. That hasn't. Someday, maybe. So have a good weekend. Work hard. Learn a lot.